Alright, so in this video, I'm going to be talking about, well, the first thing I'm going to be talking about is glycolysis, which is the first phase of cellular respiration. And glycolysis can go two ways. If there's no oxygen involved, that becomes fermentation, which I'll talk about later. And then if there is oxygen involved, it goes into the Krebs cycle, which I'll also talk about later. Or the citric acid, it's either or, the same thing. And then and then that goes into the electron transport chain, which I'll talk about later also. Alright, so glycolysis, including oxygen, you start off with glucose, which is C6H12O6, and you start off with that 6-carbon molecule, which is then broken down in a phase called the guy in the video that I saw, he called it the investment phase, because you invest 2 ATPs to break down that 6-carbon molecule into 2 separate 3-carbon compounds, which now has a phosphate group attached because of the use of that ATP. And that two 3-carbon compounds are known as pGAL, like each separate is known as pGAL, which is a phosphoglycerolaldehyde, I think, phosphoglycerolaldehyde, which is pGAL for short. And then, okay, so once you're there at that 2 3-carbon compounds, you go through a payoff phase, which is what the guy in the video called it also. And in that payoff phase, as a payoff phase is occurring, you generate 2 ATPs and NADHs, because the NAD plus gained a hydrogen, so that becomes NADH. And once the payoff phase is completed, you end up with 2 pyruvates. I'm pretty sure it's pyruvates, or also known as pyruvic acid, which starts off the Krebs cycle, which I'll be talking about right now. And so all this is occurring in the cytoplasm of a cell, just to let you know. Yeah. So in the end of glycolysis, after everything's done, you get a net gain of 2 ATPs, 2 NADHs, because the NAD plus gained that hydrogen, so that becomes NADH, and you end up with 2 pyruvates, which is used in the Krebs cycle or citric acid cycle, right? Okay, so we just finished with glycolysis, and now we're about to enter the Krebs cycle. Okay, so at the end of glycolysis, we were left with 2 pyruvates, which is a 3-carbon compound. So in total, we're left with 6 carbons. And alright, so I'm going to be focusing on one of the pyruvate groups. Okay, so in order for pyruvate to enter the citric acid cycle or the Krebs cycle, we have to oxidize it. So in this process, which is known as pyruvate oxidation, one of the 3 carbons in pyruvate is snatched away, so you're left with 2. And that carbon that was snatched away becomes CO2, or carbon dioxide. And also in the process of oxidation, pyruvate oxidation, NAD plus is reduced to NADH. So now, after you're done prepping pyruvate to enter the citric acid cycle, you're left with acetyl-CoA, which is basically 2 carbon. It's a 2-carbon compound. All right, so once you're at acetyl-CoA, a oxaloacetic acid, which is a 4-carbon compound, joins the it's merged with acetyl-CoA, which is a 2-carbon compound, and you end up with a 6-carbon compound molecule, which can now enter the citric acid cycle. And as it enters the citric acid cycle, NAD is reduced to NAD plus. NAD plus is reduced to NADH a total of 3 times in that cycle alone. And in the process of those 6 carbon compounds, you're losing one molecule, and another CO2 is formed, and then you lose another carbon molecule, and another carbon dioxide molecule is formed. And then there's a stage where FAD is reduced to, or ADP is transformed into ATP, and then FAD is reduced into FADH2. So yeah, you're done with you're left at the 4, which is a oxaloacetic acid once again. And then of course the Krebs cycle occurs twice, once for each pyruvate compound that we started, or that we ended off with in glycolysis. So you start off one and you end it, and then you go through it again. So the second pyruvate compound is now joined with the 4 carbons that were left from the first pyruvate compound that entered the citric acid cycle, and it goes through it again, producing more NADH, ATP, and FADH2. Okay, so all this occurs in the Krebs cycle takes, it occurs in the inner space of the mitochondria. All right, so in the end, you get a net gain of 4 ATPs, which is what's I gonna do? Okay, so you get 2 ATPs just from the citric acid by itself, but then you also had 2 ATPs that were produced in glycolysis. So you end up with a net gain of 4 ATPs at the end of the Krebs cycle. You end up with a net gain of 10 NADH because you started off with 2 NADH, which is in the prep. Like, as the pyruvate is being prepped to turn into acetyl-CoA, you gain 1 NADH for each group, so you're left with 2. And then in the process of the citric acid cycle, which occurs twice, you gain 6 NADH, and so yeah, you gain a net gain of 10 NADH, and then you gain 2 FADH, which you gain once in each cycle of the Krebs cycle. Okay, so net gain 4 ATPs, 10 NADHs, and 2 FADH2. And so yeah, now you're done with the citric acid cycle, and you enter the electron transport chain, which is where those NADH and FADH2 are transformed into ATPs, which is where you get the most ATPs from. All right, so now that we're done with the Krebs, let's move on to the electron transport chain. Okay, so we're now at the third and final stage of cellular respiration. I almost forgot what it was. Okay, so we're at the electron transport chain. So if you remember, or you can recall, at the end of the Krebs cycle, the citric acid cycle, we were left with 10 NADH and 2 FADH. And on average, NADH can produce 3 ATPs and FADH can produce 2 ATPs through the process of the electron transport chain. All right, so first, to start off, we oxidize NADH and which becomes NAD plus, and plus it becomes NAD plus a hydrogen and the 2 electrons. And those 2 electrons are they fall down quanta, which is energy levels. They fall down as they fall down the quanta, they go through these 2 molecules, which are coenzyme Q and cytoelectron C. And as they're falling down, they are releasing energy. And okay, so I'll go into what the energy is used for later on. Okay, so they're dropping quanta, and then it ends up at 2e negative, 2 electrons negative, plus the hydrogen proton, and plus a half of oxygen, plus half of O2, which is reduced to become H2O. I'm sure that made sense or not. All right, so oxidation is loss of electron. So NADH goes back to NAD positive because you lose the electron that it had gained previously. And those electrons, they start dropping energy levels, and then as it drops energy levels, it is reduction. It goes through reduction, which is reduction is gain of electrons. It goes through reduction to produce H2O. All right. Okay, so like I said earlier, energy is released as those electrons drop quanta levels, and that energy is used to pump hydrogen protons from the matrix, which is like the inside of the cystae, cristae. I think it's okay. I don't. So yeah, it goes from the matrix into the outer compartment between the cristae and the outer membrane of the mitochondria. So those hydrogen protons are now there, but since they're there, they want to go back in to the matrix. So if they do go in, they go in through a protein called ATP synthase, and as the hydrogen enters the protein, goes through into the matrix, it rotates this axle, which is on the ATP synthase, and as that axle is rotated, it produces ATP. So it's kind of like a water wheel, or I think a water wheel. Like as water is pushed down on it, it rotates, and that's basically how the axle of the ATP synthase works. And then underneath the ATP synthase, you have this like holding area, which is where ADP and the phosphate group are there. I think as the axle twists, the ADP and the phosphate group are like joined together to form ATP, which is where you get the rest of the ATP from, and most of the ATP throughout cellular respiration. Okay, it's a lot to take in, right? But okay, so basically electrons from the NADH and FADH2 are used. Okay, so the electrons from those 2 are used to reduce oxygen into H2O, which is a byproduct. And as the electrons fall in quanta level, they release energy as they go through the coenzyme Q and cytochrome C. So they release energy as they go through those 2 molecules, and that energy is then used to pump hydrogen protons from the matrix into the outer compartment of the mitochondria between the cristae and the outer membrane. And but like I said, the hydrogen protons want to go back into the matrix, so they go through the whole process of possibly getting through the ATP synthase. And like I said, as they go in, they rotate the axle, which then combines ATP and the phosphate group, which are in the holding area, together. So ADP and phosphate, boom, and that forms ATP, and which is where we get the most of our ATP from. All right. So overall, we like if everything's perfect. Of course, not everything is, and nothing is, right? So if everything was to be in a perfect conditions and everything, we would end up with where did I put myself with 38 ATPs, but because generally, but not everything is perfect. So yeah, we would end up with 34 ATPs just from the electron transport system, and 2 ATPs from the Krebs cycle, which is 36 now, and then those 2 ATPs from the glycolysis early on, which is another 2 ATPs. So we're end up at 38. That's if everything is perfect and everything, right? But of course, nothing is. So if everything's good and all that, we end up with 38 ATPs just from one molecule of glucose. All right, and that ends my cellular respiration process. And now I'll talk about fermentation right now. Okay, so now I'm gonna talk about fermentation. So fermentation occurs when there's no oxygen involved in glycolysis, so it cannot go through the Krebs cycle or the electron transport chain. So fermentation occurs, right? Fermentation is used in many types of foods, drinks such as alcohol. I think yogurt is one of them that uses fermentation. And so yeah, alcohol is used, or fermentation can be used in alcohol that we drink. Oh, I know, right? I'm 19, but all right. So the one I'm be focusing on is lactate fermentation. So what occurs with the pyruvate is that NADH reacts with pyruvate, and pyruvate gains 2 electrons. So it combine with a carbon oxygen bond is, and then that leads to a hydrogen getting. Okay, so when the 2 electrons combine with the carbon oxygen bond, the oxygen bond can just leave it or take it and possibly bond with a hydrogen atom that's nearby from another water molecule or something. And if that happens, then that leads to lactate, which is where it gains the hydrogen, and that leads to NADH becoming NAD positive. That's it.